Welcome back to our second installment of Deep Time. Today we're going to talk about radiometric dating, which is the dating of objects using their radioactive properties. Now, if you've had some chemistry, you've probably already learned a little bit about this. This is a picture here of my wife and I sitting underneath a dolmen in Ireland, in Northern Ireland, and a dolmen's kind of it's a really interesting looking rock structure. It's been erected like that. It's astounding. Like, how did people put that stone on top of those other stones? It's kind of similar to Stonehenge, and there's a lot of these all around the countryside in Ireland. And I put this picture up here because if you look at it and you think about this, there's a couple of dates that might be in question. We could ask, how old is this thing? But really, that's two separate questions because there's the question of how long ago was it that that rock was placed on those other three rocks, and then there's the question of how old is that actual rock itself, and the ways of going about answering those questions could be kind of different. Archaeologists are going to use one method. Paleontologists, geologists are going to use another method to try and date the actual rock. So today we're going to talk about those dates, and oftentimes when I start talking about radiometric dating, I will have folks ask me lots of questions about, how old the Earth is, and we'll try and talk about that some today. But as a geology teacher, as a paleontology teacher, a science teacher in general, I have a lot of folks that say things to me like, I just, that's great, Hambling, but, I just really don't believe that the Earth is older than about 2,000 years, or, I just don't believe that climate change or global warming is a real thing, or I just don't believe that evolution happened or is taking place or is even a real thing. Or maybe I just don't believe that the Earth is round. I've even heard that one. And more recently, things along the lines of, I just don't believe that masks actually work, that they do anything in terms of our current pandemic. So, what I would say to that is, this is America, and our country is founded on the basic principle that everybody's beliefs matter and everybody can have whatever belief they want to have, and that is most certainly, definitely true, and needs to be so in a free society like ours. But there's also kind of a simple fact, and that is that, if your beliefs conflict with current scientific fact, oftentimes you're going to be in for a rude awakening. Something along the lines of your belief in how old the Earth might be is probably not likely to affect you throughout your life. It's probably not going to matter that much unless you're in a room full of scientists and trying to talk about the age of the Earth, right? But your belief in other things could have serious consequences. Your belief in whether or not masks work and help protect you and protect others against the current pandemic that's going on. Well, that's a very real thing that has real consequences. Your belief in whether or not radiometric dating is possible kind of questions the foundations of our understanding of nuclear physics, and you can disbelieve all you want in that nuclear weapons are a real thing and can have real dire consequences, but if a nuclear weapon were to be detonated, we'd all find out very rapidly just what consequences that would have. So scientific understanding is foundational, right? In these questions, they do have consequences. So I hear a lot of this stuff, and I wanted to, I've got so many stories about people asking me questions like this and making statements to me about, I just don't believe this or I don't believe that. But one really stands out in my mind, and it happened actually when I was in Ireland with my wife. We spent 3 weeks traveling around the Irish countryside, met a lot of really wonderful people, saw some absolutely astounding and amazing places. It was great. We rented a car to go around Iceland. It was kind of a junker, to say the least. We referred to it as our clown car because it looked like at any point in time, if you stopped it and got out, about 16 clowns would come out after you. It was so small. It was so tiny that There is no way that it would be ever be sold in America. Nobody would ever be caught dead driving a car as small as this. It was just barely big enough to fit the two of us in the front seats, with room in what was sort of a back seat for our two backpacks, and that was pretty much it. It was a pretty funny little vehicle. In fact, we even lost the brakes off of it at one point in time, and that was very interesting. But anyway, we traveled around the countryside, staying mostly in hostels, different hostels. And if you've never stayed in a hostel before, hostels are a really cheap way to visit other countries. If you don't have a lot of money, it can be anywhere from $15 to $25 or $30 for the night to stay there. But you're oftentimes sleeping in like a big dorm room with maybe 10 or 15 other people in the same room, and then you have like sort of a shared shower or something like that. But they're all a little bit different. So anyway, as the story goes, we're driving up through Northern Ireland, and we stop off at this little hostel, and we get out and we're kind of checking in. We're meeting the woman who owns the place, and she says something to us that's really kind of bizarre. I've never heard before. She said, this is a great place. Like, I'm really happy to have you here, but I have to kind of warn you about one of our visitors. I kind of looked at her like, what? And she says, well, we've got this guy staying with us. His name's Stephen, and he's a little bit different. And if he says anything strange to you or anything like that, don't really worry about it. He's completely harmless. Wouldn't hurt a fly. But it's really no big deal. You'll probably not even see him because he's out riding his bike right now. He'll probably not even be until late tonight. So now like two things are going through my mind. Like, first of all, like, I want to meet this guy, and secondly, I'm thinking, like, I'm not sure I want to sleep tonight in this room full of people with some person who I don't know really anything about and is sort of sketchy, right? So anyway, as it turns out, he comes back sort of later in the evening before we're to bed, and I got to meet Steven. He seemed like a totally fine guy. We chatted for a little bit. He asked me kind of like where my wife and I were headed out to in the morning, and I told him, well, we're going to head further north because we really want to get up by Giant's Causeway. We want to see Giant's Causeway. We want to see kind of the northern part of Ireland, further in, like up by the coast. Kind of explained to him where we were going, and seemed like kind of a great guy. And in the morning, we woke up and took off and headed up north towards the coast. And we get up there, and it is just absolutely pouring rain. And it just rains like it does in Ireland for just hours and hours and hours. And we don't care, we've got our rain jackets, and we do what we normally do. We throw our rain jackets on, and we head out, and we go where we want to go. And we went for a hike across this really cool suspension bridge out over the ocean to this tiny little island, and came back and had dinner in this pub. And we're leaving the pub, and we head back to what's going to be our little hostel where we're staying for the night. And then we're kind of in the middle of nowhere. There's like really nothing up here except this one little hostel. And we're going to check in, and it's just empty. And right behind us walks in Steven. This is kind of strange, because it had been pouring rain for hours and hours, and Steven's mode of transportation was a bicycle. And we drove at least an hour to get to where we were at, so I don't know how long like he had been out in the rain riding that bike, but it had been a long time. But he went up there, apparently because we were going up there, and he wanted to visit with us, and they decided to stick us all in a room together. So once again, I'm like worried about going to sleep for the night. And he's asking me questions about, what I'm doing in the morning and whatnot. And he says, I tell him I'm going to go up to Giant's Causeway, it's an amazing place, right? It looks like this. And I'm explaining to him that we're going up here in the morning, early, want to get up there before there's any people out, and we just really want to see this place. He's like, I'd really like to go visit that place too. Do you think like I could come along with you guys, because I don't want to try and ride my bike in the rain, because it of course was still raining in the evening, and it was probably going to rain in the morning because that's what it does in Ireland. And I want to be a nice guy to him, so it's like, sure, we'll take you along with us. And so in the morning, my wife and I empty our backpacks out of the back seat, and he crams himself in there because it's just tiny, tiny, tiny. And we're driving out to Giants Causeway, which is, I don't know, it's about 15-20 minute drive or so from where we're at. And it's early in the morning, and we're chatting away as we go. And Stephen kind of is asking me, so what do you think about that place? How in the world? It's so bizarre. Like, how could something like that even form? Like, it's such a mystery, And you look at it, and it is amazing, right? And so I'm trying to explain to him sort of how this is columnar basalt, and this area used to be, its ancient area, it used to be underneath the ocean, formed, like tens of millions of years ago. And this basaltic lava flowed out, made the ocean floor, and it actually goes all the way through up to the coast of Scotland. Like it's all the way underneath the ocean still. And then because of uplift, it got brought up like that. And he's like, well, how does it look the shape that it looks? And I said, well, sometimes when basalt cools, it cracks in these like really bizarre hexagonal patterns like this. And it's only visible to now because of, plate tectonics and uplift and whatnot. And he just kind of stopped for a second. He says, well, do you really think it's that old? And I said, well, yeah, I think it's, like tens of millions of years old. And he said, well, I just don't believe that. I don't believe that, it could be that old. The Earth's not that old. And he's kind of going on. I got real quiet because I'm like, I don't want to get into it. I'm here to have fun, enjoy myself. I'm not here to teach science. So we're driving along, and he's kind of going on. He says, well, I just don't believe in that carbon dating stuff. There's no way that you could carbon date those rocks there. And then I picked up on that. I said, but you know what? You're absolutely right. There is absolutely no possible way we could carbon date those rocks. That's basalt. There's no way we could carbon date that. And he said he was kind of happy with that, and I didn't really add the rest, which is the fact that you can only carbon date things that have carbon in them that were once alive because of the way that carbon dating works. But we know pretty much for a fact that Giant's Causeway is 50 to 60 million years old because of other radioactive elements that we date in the rocks, not because of carbon dating. But anyway, I was hoping I didn't make him too angry because this place is pretty unique, and it gets pretty steep in some spots. I'll show you some pictures here as we go, but it's just absolutely beautiful like this. You can see this is it's just a gorgeous landscape, and it was raining, of course, on us. Not too bad at this point. We're walking around all these things. If you've ever seen the cover to the Led Zeppelin album Houses of the Holy, you have seen a drawing of this particular location. Here's my lovely wife and our good buddy Stephen that we met out here walking along this here, and then you can kind of travel and head up towards the cliffs area. So you can see if you look down below, most of that rock underneath of us is actually columnar basalt. I think that's my wife out there on the edge of that cliff right there. There's no railing, right? You're just walking along the side of this coast, and it's absolutely astoundingly beautiful. But I kind of tell you guys this stuff because it's not just students who have these questions and sort of want validation for their beliefs in certain things, but other adults do as well. And it's not really the job of scientists to validate what you believe. Like I said, it's a free world, and you're welcome to believe what you'd like to believe, but keep in mind there's consequences for disbelieving something that it has been essentially proven to be scientific fact. So will that affect Stephen throughout his life? Probably not, right? The guy could probably go out through his whole life without really understanding how old these rocks are or how they formed. But other things, that scientists discover and show us have real world consequences, right? So let's delve back into sort of radiometric dating and how this works. So if we take a look at radiometric dating, the way that this works is that we have to use radioactive elements that are known to decay at a fixed rate. So it's not random. It's not that we don't know how often these things decay. We know very, very well. And I know it's confusing for folks because we're dating things that might be, say, millions of years old or even billions of years old. And everybody knows that humans can't wait around to run an experiment that runs over millions or billions of years. So We take averages. We look at the decay of materials over certain periods of time. We look at our understanding of chemistry, nuclear chemistry, and we get it right, right? So when we're looking at radioactive decay, we're assigning an actual numerical age to a rock unit. We're saying this rock unit is 12.1 million years old. This rock unit is 1.26 billion years old. That's very different than relative dating. So the two kind of go hand in hand. If you know the relative locations of some rock strata and you know the absolute numerical radiometric date of one of those units, you can easily say that the one above it is younger than that and the one below it is older than that. So we start to assign dates to everything on our planet through this method. So the way that this works is that when a rock first solidifies, think of an igneous rock like a granite or a basalt, something that formed out of a melt. This is material that was molten. So it could have been lava, could have been magma, and it starts to cool. Once it cools, it locks in the clock. So as soon as it hardens, as soon as it is solid rock, it's now fixed. And the reason for this is that as it's molten, there's all sorts of stuff in there, right? There's all the different minerals that are going to form, and some of the minerals that are going to form in there will contain radioactive elements in them. Okay. Now, keep in mind the whole rock is not radioactive. We're not just only able to date rocks that are uranium or uranite or something like that. It could have just a very, very tiny amount of it in there. In fact, most of them do, a very, very tiny amount, or we'd all be irradiated and dead right now. So as long as there's a little bit of radioactive element in there, which there pretty much always is, we can use the rate of decay of that element to get the date of the rock. But the point is that the clock starts ticking as soon as that igneous material hardens, as soon as it freezes from liquid to solid. Because what's going on is that any decay that's happening, the element is essentially escaping from that melt until it's hardened. So once it's hardened, any daughter material that's formed stays inside the rock, and we can collect it and see how much there is. So let me kind of go back to that point here for a second. If you had chemistry, this is going to seem really basic here, but follow along with me. So there's a certain amount of material inside any rock, for the most part, that's radioactive. Let's say that there's some radioactive material, some uranium, inside of a rock. The whole rock isn't radioactive, but to start with, 100% of the material that's radioactive in the rock, not 100% of the rock, 100% of the material that's radioactive, 100% of that is called the parent. So it hasn't decayed yet. As it decays, the atomic nucleus falls apart and the atom changes into a new element, a different element, in a different location on the periodic table. And so we call that element it changes into the daughter. So the parent material decays into the daughter. Now, to figure out how much time has passed, all we need to do is measure the relative abundance of parent as compared to daughter material, and it will tell us how much time has passed. And we do this in terms of what we call half-lives. So a half-life is just the amount of time it takes for half of the parent material to decay into the daughter. So in the picture here, if we start out, it starts out with 100% parent. You can see that there, it's a 16:0 ratio there. And after one half-life, exactly half of that material has decayed. So in the next picture over, you can look at the atoms down below, and we've got 8 of them are parent and 8 of them are daughter. Now if you reduce that, you'll have a 1-to-1 ratio, which is what we would talk about. So the parent to daughter ratio after one half-life is 1-to-1. Follow? But the pictures are showing you as the whole thing, it's not reduced. So if we're talking about in terms of, let's say, that happened to be potassium-40 that was in there. Well, potassium-40 is going to decay into argon-40. And that takes about 1.277 billion years, right? So at the point that you have 50-50 in there, or 1-to-1 ratio, 1.277 billion years has passed. Now, we don't need to wait that long to get a date. We can get dates that are younger than that because, well, some is still decayed, but not half of it, right? So it's really just a formula to figure that out, and we just look at ratios. And as more time goes by, more decays. Now, if you're looking at this and thinking, well, at some point, well, isn't all of it going to decay? Kind of yes and no. I guess the real answer is that at some point, enough of it will have decayed that we won't be able to get an accurate measurement of how much is left. So every one of these isotopes that we look at here has a range, and that range only is specific for a certain time period. In other words, enough time has to have passed for enough of it to decay that we can measure it, and also too much time hasn't passed so that there's not enough left to measure. Follow? So that's why we have dating ranges on some of these things. So you can't just use any radioactive isotope to date any material. If it's really old material, you've got to use a different isotope than if it's much younger material. And that's why I kind of gave you some of the date ranges here. If you take a look, and there's loads more isotopes that we use in dating than this. Ludium has got a dating range of somewhere greater than about 10 million years. There's a bunch there that are about 10 million years. If you look down at potassium, you're looking at about 10,000 up to about 3 billion years. So that's a pretty big range there. And like I said, there's loads more, and I put the material that we're actually dating. So in order to date something with uranium-238, you need to find some zircon crystals in it, or some uranite crystals in there. And turns out those zircons are fairly common, so it can be something to easily use. Now, how do we know, and we'll come back to this in a little bit, but how do we know that the date is accurate? Well, think about the check on this. If you can date something with both uranium-238 and uranium-235 and rubidium-87 and some ludium-176, and all of those dates come out the same within a degree of error, that is some pretty astounding evidence that this dating mechanism is working really well. I mean, you used 3 or 4 totally different elements and got the same date. That's some pretty good evidence, right? I don't need much more than that to accept that this is actually working. We'll come back to that concept, though, because we use other things to sort of check our clock. Now, I think we've talked about parent, we've talked about daughter here. We've got, like I said, we've got to pick the right element depending on how old the material might be. Make sure the element is present in there that we're going to be measuring. But there's some other issues too. If you think about this, the type of rock that forms from a melt is igneous rock, right? So what if you tried to date some sedimentary rock? Well, you're going to have issues because the sedimentary rock is made up of a bunch of bits and pieces of other rock. So yeah, you might be able to date each individual little nodule, each individual little rock inside of the sedimentary rock, but you're going to get a whole bunch of different dates. They're all going to be different. If it's sandstone, each little grain of sand might have a totally different date. So it can be very difficult to use this to date something like sedimentary rock. Metamorphic rock is a little different. Some metamorphic rock we can actually date pretty well this way. For instance, these zircon crystals tend to survive getting squished and cooked. And so you could date a zircon crystal if it's found in a metamorphic rock. But we've got to be careful with that because when metamorphic rocks are formed, we're squishing and cooking pre-existing igneous or sedimentary or some other type of rock. And if you squish and cook it enough and melt it, you've completely reset the clock. So you might ask the question of, well, what happens if you've got an igneous rock and it gets completely remelted? Well, guess what? You just reset the clock. It's now at 0 time because it starts from when it was liquid and then this clock starts ticking as soon as it's hardened. So we have to kind of keep that into account when we're dealing with these things. Now, before we go on, the one last thing I want to talk about is this carbon-14 dating, which is what Stephen had brought up in our little trip through Northern Ireland. And carbon-14 dating it still relies on the radiometric principle of radioactivity. It's really similar in a lot of ways to these other dating techniques. However, it's got one really big difference. Well, maybe two. The first difference is its dating range is really only good for about 100 to about 50,000 years. So if we're talking in terms of tens of millions of years, like that columnar basalt I showed you a picture of, this just ain't going to cut it, is it? Like, it's not even going to come close. Like, the clock will be burnt out before you ever even come close to the age of the actual material. It will have all decayed. So that doesn't work at all. Now, the other big problem with carbon-14 dating of geological materials is that carbon-14, the clock operates a little differently. What we're actually measuring is radioactive carbon. So it turns out that everything that's alive has some radioactive carbon in it. And the reason for this is kind of goes all the way back to plants. So a little biology lesson for you here. So plants take in carbon dioxide out of the air, and they string the carbon molecules together in photosynthesis to make C6H12O6, which is glucose, which is sugar, right? So the carbons are strung together out of the air. Now the air, our air that we're breathing, contains a tiny bit of carbon-14, which is radioactive carbon. Don't fret, there's not that much there. You're going to be okay. Most of it's carbon-12. So this carbon-14 gets taken up by the plants, okay? While the plants are alive, they're continually replenishing their carbon-14 supply. So even though it's decaying inside their bodies, they're still taking more in from the atmosphere. So the relative abundance of carbon-14 is always staying at roughly exactly the same as it is in our atmosphere. Follow? Now, as soon as a plant dies, it stops taking in new carbon-14, and the carbon-14 is still continuing to decay at the regular rate, which means that now, if we measure the carbon-14 present in the dead plant, it's going to be off from what it is in the atmosphere. Now, all we really need to know is what the carbon-14 content of the atmosphere is, and we can compare that with how much is left in the plant, and then we can arrive at a date. Now, this is a little tricky, and this is why carbon-14 dating was a little contentious when it first was discovered, is that how do we know what the carbon-14 levels were in ancient atmospheres? They could have been different than they are today. So that's a question that scientists had to answer, and something that we had to look carefully at when we were fine-tuning the carbon-14 dating method. And yes, it has been fine-tuned, and we keep adjusting it. The more we understand the carbon contents of different atmospheres in the past, the better we can fine-tune that carbon-14 dating method. But if you look at it, it doesn't go that far back anyway, so you can roughly assume the carbon-14 level was pretty similar to what it is today. So anyway, take it at face value here. Carbon-14 dating is very accurate. We have very carefully tuned that scale, but it is different than dating igneous rock. Follow? Because there's never, even if there's carbon in that igneous rock, it was never alive. It never came from a living thing. So it's not going to contain the same abundance as what the atmosphere contained. Now, how do we date things like human bones and things like that using this method? The reason is because as alive as a human you are, as you're alive as a human or any other animal on the planet, you're eating plants or other things that ate plants. So your carbon-14 content is identical to the atmosphere until you pass away, and then your carbon-14 clock starts ticking. So when we date archaeological sites with carbon-14, we're dating the point at which the organism died. And so we date from there. That's why we can date things like charcoal from an ancient campfire or something like that, because when the plants died and were burned, that's when the clock actually started. Burning doesn't remove the carbon-14, right? That's what's left behind is all that carbon in the campfire char. So we can date things like human remains, animal remains, plant remains, ancient campfires, things like that. We can even we can date a lot of stuff along those lines. We can even date things like ancient coal deposits because that came from living material that decayed in a swamp, right? So super useful, but yet really different in some respects than, say, uranium dating. So anyway, that's my explanation of carbon dating versus uranium or rubidium or any other type of dating. All right, let's keep moving here. So like we said before, radiometric dating gives you a time that the mineral began to preserve all the atoms of the parent and the daughter isotopes. So this is the time at which it cooled. Okay, if you reheat the rock, then you reset the clock. So this is really, it only works for igneous or metamorphic rocks. Even then, those metamorphic rocks, like I said, sometimes you'll have crystals in there that will survive, like zircon crystals, which is one of the ways we actually arrive at the age of our planet. We have found 4.4 billion year old zircon crystals in Australia, in some slightly metamorphosed rock. Truth is that most of all the old rock on our planet, the cratons in the very bottom, is really all metamorphic rock. It's been here so long, it's been squished and heated and cooked so many times, right? And it's difficult to do something like directly date a sedimentary rock. We've got to use different methods. We've even brought back zircon crystals from the lunar crust, and that gives our moon date at about 4.3 billion years old. From the Apollo missions, right? That really did happen. No conspiracy theories here. We went to the moon. We brought back actually loads and loads, like hundreds of pounds of rocks we brought back from the moon, and they're in places in NASA. And you can actually look up the pictures on the internet of those rocks. It's kind of pretty cool. So let's talk about another thing that we date on the moon, which is kind of interesting. We can actually know when a crater was formed on the moon, because what happens when a meteorite impacts the moon's surface is it heats up and remelts the rock that it hits, leaving behind a reset clock, right? If you have an impact that's so intense that it completely melts the parent material there, you reset the clock. So if we go up to the moon and we bring back moon rocks from inside of a crater where the material's been melted by the meteorite that hit it, we can then look at it and get the date of the actual crater, the impact crater. It doesn't give us the date of the moon. You know, if we go someplace else where there's not a crater and get material that wasn't remelted, we can get the date of the moon. So, very different thing, right? We've got to be careful with what we're gathering. We've got to know what we're collecting, know what kind of rock it is, things like that. Okay, so let's take a look at some other methods that we actually use to date. Turns out that there's a lot of different methods other than just radiometric dating to give us the ages of different things. For instance, we can take the radiometric dating scales and correlate them with each other and be very content that they give us the same ages for things. But how much more so content can we be if we have other methods that are not even dependent on radioactivity that give us similar dates? And they do. So we can look at, for instance, dendrochronology, which is the study of tree rings, both living and fossil. We have fossilized trees preserved out in the Southwest, and that fossilized tree material has rings in it. We can count the rings, we can line those up, and we can get dates that give us similar dates to carbon dating. We can count varves in ancient lakes. Glacial lakes will put layer after layer of silt down, and it turns out that it does it every single year. And so we can literally count back year by year by year and get dates of formation. If those match up with dates of material, say a volcanic eruption that was radiometrically dated, we can be really happy, and they do. Another method of dating, which I've got a picture of a crater here that was actually dated this way, is something called thermoluminescence, which is really kind of cool. As it is, rock-like quartz that's got a lot of silicate material in it is really good at trapping electrons from cosmic rays. And these things bombard us continually because the sun, right? And they hit the Earth's surface. And as long as the rock is exposed to the surface, at the surface is not buried, the silicate rock, like quartz, starts trapping these electrons from these cosmic rays. Now then all we need to do is start counting, how many electrons it's trapped, and we can get a date for the rock just based on how long it's been exposed at Earth's surface. The other thing that resets this clock is when you heat it. So if you heat something like a flint tool, as a lot of Native Americans did, they'd heat their flint up before they would flint knap it, or firing pottery, which contains silica sand in it, you heat it up, you reset the clock. So something like a meteorite impact on Earth heats up the rock enough that it will reset the clock. And so if you check that stuff, that material, you can actually get the date of it based on cosmic rays. So it's kind of neat. So that's how we know that Meteor Crater, which is this is a picture of in Arizona, is actually 50,000, roughly 50,000 years old. Using that and, of course, some other dating techniques, we can come up with the fact that this is one of the younger meteor craters, or meteorite craters that's been left on our planet, which is the reason that it's not all eroded away. Most of them are long since buried. This one came from an iron nickel meteorite that was about 50 meters in diameter, moving at about 29,000 miles per hour. The crater in front of me, if you kind of get some scale there, is about a kilometer wide. That's pretty big. And it's 170 meters deep. So multiply that by about 3 if you want feet. It's a pretty deep crater. If you look down there at the bottom, you see that little white patch right in the middle of the crater. Turns out that when they first discovered this and realized that it was a crater from a meteorite, the folks that owned it or purchased it, the Beringers, decided that they would try and mine to see if they could find that meteorite material, because it might be worth a lot of money, right? They didn't really know what might be in the meteorite, but they knew that meteorites contained iron and nickel, and just the iron and nickel alone would be worth a lot of money if you could recover it. Think how big the rock was that made this thing, right? We know it was about 50 meters in diameter. That's a lot of iron and nickel that you could sell. So they assumed that that was actually buried down there underneath all of this rock that had been blown up out of the crater. So they erected a mine shaft and they started digging, and they dug like 3 holes. I think the deepest one was somewhere around like 1,000 feet deep or something like that. They even thought they found something, but turns out they never actually did find any of the original meteor in the bottom of this crater. Now some of it has been recovered. Turns out that almost all of it vaporized on impact. So imagine the explosion that took place here, right? It blew this giant wall of rock up out of the desert. You can see back behind the crater how flat it is. But they did that. One of the largest pieces ever discovered was this one right here. And it's iron nickel. If you put a magnet on that, it would stick to it. It's a pretty good sized chunk. I don't think a person could easily pick that up. It was heavy. That was probably like, I don't know, like 3 basketballs in size. But they literally spent 27 years digging this hole in the bottom of this crater and never ever found any meteorite. This piece, along with a whole bunch of other pieces of fragments, were actually found in sort of the surrounding plains of the desert, and they broke off before the impact ever occurred. So they didn't get vaporized. There is material from the meteorite, so we can date that directly and know how old the meteorite is itself, which is a different date, of course, than the age of the crater. So we get dates like that as well. But let's talk now about some of the periods and eras and eons of geological time. So we organize geological time in a series of chunks, mostly based on not just what lived there, but oftentimes based on extinction events. That way we can see it very clearly in the fossil record. But here are the major eons of Earth's timeline. Let's start from the bottom and kind of go through them here. The first one starts down there at about 4.6. GA stands for gigaanna, so it means billion for Americans. So this is known as the Hadean or the Hell eon. So that's an apt description when you consider that Earth forming from its earliest bombardment was essentially a molten ball of hell. And at this time, all the heavy elements are sinking to the Earth's core. That's called differentiation. And all the lighter stuff like silicate material that's going to become quartz and granites and stuff like that's floating up towards the top. This is also kind of towards the end of this eon is the formation of our earliest oceans and what we call our secondary atmosphere. So all those volcanoes and things that are spewing out gases are forming our secondary atmosphere. The first atmosphere that we had was probably hydrogen, helium, pretty similar to what the sun's got, but that stuff was boiled off pretty rapidly. So still not like oxygen like we have today. It would have been pretty darn hostile. And then we could move up. At about 3.8 billion years ago, we reach what's known as the Archean, or the eon of ancient life, or just ancient eon, I suppose it's called. This is kind of marked off as the very first appearance of life forms in the fossil record, and they are just little cells, little bacterial cells that we see in the fossil record. The continents also form at this time, so they're kind of smaller, and they're moving around a lot faster than they are today because the Earth is a lot hotter. Plate tectonics is moving at a much faster, more rapid rate. But this is the appearance of the very first life at about 3.8 billion years ago. We've got some evidence that the first fossil life existed. Then it's bacteria, so it's nothing too super exciting. Then comes what's known as the Proterozoic. Okay, so this roughly translates to before life. It starts at about 2.5 billion years ago, and life at this time consists of single-celled creatures, for the most part, bacteria that are building up our atmosphere. They're building up our oxygen, and we see oxygen levels increasing throughout the Proterozoic. Tectonic plates start to form, so we've actually got plate boundaries now, these things moving around. And near the end of this, we see the first multi-celled life, which is also not very exciting in the fossil record. It's like little clumps of cells. So not super duper exciting yet. But we're starting to get pretty close. Well, actually, let me correct that. In the Neoproterozoic, there, right near the end of the Proterozoic, we do start to see some kind of interesting looking multi-celled creatures. Some really weird things that we'll never see again, that are just really bizarre sort of life forms, and maybe even some that kind of will represent some of the shapes of later life. So we'll talk more about that later, and we'll look more closely at what some of those weirdo creatures used to look like. But most of them are soft-bodied. There are some little or smaller things that are not, but for the most part, it's very soft-bodied stuff down there at the end of the Proterozoic. So then we come into the Phanerozoic, which translates to visible life. So we're now at about 542 million years ago, all the way up through the present, includes the Phanerozoic. So this is life that we can really start seeing now. We kind of mark this off as the appearance of like hard shelly material for the first time. We see a real rapid diversification of life. Life just explodes in this time period. It's marked off at the boundary of what we call the Cambrian boundary. So the Cambrian is actually a period, which actually is over on the right there. You can see, Cambrian down there at the very bottom on the right, the Paleozoic. It's kind of a blow up there. In fact, we call all of that eon at that time, going all the way back to the Hadean, all the way up to the end of the Proterozoic, refer to that as the Precambrian, because that's the time before the Cambrian, if you will. It was thought for a long time that life started in the Cambrian, but now we know differently. We know we had life going on way, way back, which isn't surprising. So let's then now break things down from eons to eras. Let's take a look at eras here. So let's go again from the bottom up. So the Paleozoic, which roughly means ancient life, starts at about 542 million years ago on up to 251 million years ago. This is a time when life is diversifying like really rapidly. So we see life in the early Cambrian there at the beginning of the Paleozoic. It's ocean life. There's just, the oceans are teeming with life, and it's diversifying like mad throughout the Ordovician. And then also, kind of in the middle and towards the end of this, life is moving onto land. This is like the invasion of land by life, and life diversifies, and we get all these different forms that looked a lot more familiar to us today. Needless to say, during the Carboniferous there, is a time when much of our coal and oil reserves are getting laid down. That stuff we're mining today, all those fossil fuels. So when you look at how long ago that was, it was a long time ago that stuff got laid down. We're talking hundreds of millions of years ago. So right on up to about 251 mega anna or million years ago, the Paleozoic life starts out in the oceans and moves on to land. Ancient life. All of our rock here in Indiana is from the Paleozoic for the most part. All the fossils you pick up out of the creek, Paleozoic, mostly Silurian, Devonian, maybe Ordovician life. So from the middle life, we call that the Mesozoic. So starting from about 251 to about 65 million years ago, this is the age of the dinos. So when you think about dinosaurs, they're much more recent than any fossil you're finding in the creek. When you look at stuff in the creek, that is some ancient life, like literally Paleozoic ancient life. The Mesozoic, which stands for the middle life, is the time that the dinosaurs ruled. Right up to about 65 million years ago when they bit the big one there and went extinct. Then begins what's called the Cenozoic, which stands for recent life. This is where we're at right now, at the end of the Cenozoic, continuing onwards, hopefully. This is known as the age of the mammals because mammals dominate. We rule the world. We're mammals, if you don't know that. So from 65 million years ago right on up to present is the Cenozoic. Let's talk now sort of about how we know how old the Earth is, right? We know that the Earth is not flat. We know that masks work. We know that evolution is an ongoing process on our planet and transcends all the way back through the most ancient of time that we can look at the fossil record. We know that the Earth is warming. We know these things. We know that masks work, right? How do we know the age of the Earth? It's a really good question. And it's more roundabout than you might think. And the reason is because old rock doesn't exist on the planet. We have some very old rock, but we don't have the oldest of old rock. So we have to utilize some different things to come up with an age of our Earth, which we place at about 4.57 billion years old. So let's kind of start from the top here. We have rock older than about 3.5 billion years that can be found on every continent on the Earth. Now that doesn't get us to 4.5 yet, 4.6 roughly, right? We're still about a billion years of rock that we're missing if we really want to place the age of the Earth. So let's take a look here. The very oldest rock that we can find on our planet is the Acosta gneiss in northwestern Canada. Okay, there's a picture of it. You might recognize that rock gneiss. Yes, it's metamorphic, so the minerals we pick out of it need to be materials that have not been cooked enough to reset their clock. So there's some details here that geologists need to hammer out very carefully. And that gives us a date of about 4.031, and I put the plus minus on there, 0.003 billion years. So this is accurate by our dating methods to 0.003 billion years. So when we round and say, it's about, our oldest rock is about 4.0 billion years, we're really accurate out to a number of decimals there, aren't we? Okay, so that's the oldest rock on our planet. Still not there yet. We're still about 0.57 away from the actual date of our Earth. That's the oldest rock on our planet. If we date the oldest meteorite that came from Mars, so we had some of this material fall to our planet, we've collected it, we recognize it's from Mars, we come up with a date of about 4.09 billion years. So that's really nice that we get that date because it coincides very neatly with the oldest rock on our planet, which tells us something that we already knew from other methods, that the entire solar system formed at roughly the same point in time, about 4.57 billion years ago. So let's kind of continue forward here. How else do we know? Well, we actually have older material on Earth than the oldest rock. The very, very oldest material that we have is about 4.404 billion years old. and it actually comes from Western Australia. These are those zircon crystals we were talking about that are found in what's known as the Jacks Hills metaconglomerate. So once again, a conglomerate is a sedimentary rock. A metaconglomerate is a slightly metamorphosed sedimentary rock, and some of you guys found a few of these. So that date is from a particular crystal that's found inside of some of the material inside of this rock. So what we're saying is that those crystals were part of an earlier rock that was since ground up, redeposited, rehardened into a conglomerate, which was then slightly metamorphosed, preserving still the zircons that were able to give us a date. So it's nice and neat that all these dates line up really, really carefully here, don't they? We've got around the 4 to the 4.4 billion year range. But let's take this a step further. We can actually date that rock material that the Apollo missions returned. And looking at the Apollo material, and yes, it's breccia, which you also learned about, because of the impacts that have happened on the moon's surface, this rock has been cracked and busted all over the place. So if we look at the material that's not been completely melted from a meteorite impact, we find a crystallization date of what we call the moon's lava oceans when the moon was molten of about 4.46 billion years ago. So that is really kind of nice. Like that, well, this is fitting really well. We would expect that date to be around that range, right? So then let's bring in here meteorites from Meteor Crater. Okay, these things show a spread of ages, which we kind of interpret as the time it took the solar system to form. So think about the material that's floating around the early solar systems, right? The early solar system. We assume it probably took about 50 million years for the solar system really kind of coalesce. And the ages of these meteors that we get from Meteor Crater, the ones that are spread out across the desert, not the whole, but the actual meteorite fragments, are about 4.53 to 4.58 billion years old. So it's interesting that that's a mixture of ages. Like, it tells us that the solar system was forming. This is the earliest material in our solar system. And finally, let's talk about the oldest material we have ever dated in our entire solar system. That material is about 4.56735 plus or minus 0.00028 billion years old. Now that's a degree of accuracy that I am very happy with, right? Take a look at that number. That's where we get the age of roughly our solar system, our Earth, at about 4.57 billion years, if you round that to a number that's easy to write down. So sometimes you hear people say, oh, the Earth is, 4.5 billion years old, or the Earth is roughly 4.6 billion years old, or people even say the Earth is 5 billion years old or 4 billion years old. They're rounding these numbers a little bit and just kind of sorting it out. But keep in mind that it's a little flexible, because are we talking about when the solar system formed, or when the Earth first hardened, or when the moon formed? Like, there's different dates here, right? But we place the age of the Earth at about 4.57 or 4.6 billion years ago. Now that is a very different date than you might hear from very different pseudosciences, right? Like, for instance, the young Earth date of 6,000 years. That is, like, really young. Like 6,000 years, I mean, it's not even a billion years. Or the flat earthers who place the date of the Earth at about 13,500 years old. Like, there's some, like, unavoidable conflicts between scientific knowledge and those dates. And like we said before, your belief in something may not necessarily affect you in terms of, how old you believe the Earth to be. But your belief in other scientific knowledge very much so could. So anyway, I wanted you to recognize how we actually come up with the age of the Earth, 4.57 billion years. That's it for today. Submit your quiz and you're good to go.